Welcome back, everyone. We're going to talk in this lecture about collisions in multiple dimensions, primarily two dimensions, but there's nothing that says we have to limit it to two dimensions. And the major difference between one-dimensional collisions and multidimensional collisions is that when we do the energy or the momentum conservation for multidimensional collisions, we have to take the vector nature of momentum into account, so that this equation, that the sum of momentum has to be constant during the collision, so that the momentum before and the momentum after for the entire system is conserved. These are vector sums, and therefore we have to break them up into the individual components, and that the x momentum must be conserved, the y momentum must be conserved, the z momentum must be conserved independently. So if you're working in two dimensions, you get two relationships out of this. If you're working in three dimensions, you would get three relationships out of that, and so on. Other than that, it works very much like collisions did in one dimension. And so let's just get some examples going here. So this one says, asteroid collision. Two asteroids of equal mass in the asteroid belt between Mars and Jupiter collide with a glancing blow. Asteroid A, which was initially traveling at 40 meters per second, is deflected 30 degrees from its original direction, while asteroid B, which was initially at rest, travels 45 degrees from its original to the original direction of A. So let's draw ourselves a picture here. So here we have asteroid A, which is moving at 40 meters per second, and asteroid B, which was initially at rest. So this is our before picture. And our after picture is that from the point of collision, now our asteroid A is moving at a 30-degree angle to its original direction, and at a speed, whatever the total speed of A is, the final speed, and that asteroid B is moving at a 45-degree angle relative to the original direction of asteroid A, and then this would be VB after. And so our after image, or after picture, would look like this. There's our asteroids A and B moving off at a 30 and 45 degree angle relative to the initial direction of motion of asteroid A. Now, you might ask, why is it that we know that B must be going down if A is going up? Well, because the total momentum of this part of the system beforehand was purely horizontal. So there was no vertical component of motion. There was no component of motion up and down. So there must, in fact, be a downward component of motion to balance out the upward component of motion. And indeed, as I've drawn these, probably the speed AF here would have to be larger than the speed BF, because AF is at a shallower angle relative to B. So anyway, our after drawing would look something like that. There isn't any energy conservation or anything to worry about here. What we're going to worry about is just conserving momentum. So let's look first at the horizontal components of momentum. And we can write down that the mass of asteroid A times the velocity of A in the x direction initially plus the mass of asteroid B times the velocity of B in the x direction initially. And in this case, the velocity of B was 0, so that term goes away. And over here we have the mass of A times the velocity of A in the x direction afterward, or final, plus mass B times velocity B in the x direction final. And if we were going to write down the y momentum conservation equation, it would look like, again, the mass of asteroid A times the velocity of asteroid A in the y direction initially. And in this case, A wasn't moving in the y direction, so that term is 0. Plus the mass of asteroid B times the velocity of asteroid B in the y direction initially. And asteroid B didn't have any velocity at all initially, so that term is 0. So that's the total y component of momentum was 0 to begin with. And so the y component of momentum afterwards must also be 0. That mass of A times the velocity of A in the y direction afterward plus mass of B times the velocity of B in the y direction afterward. And again, just to remind ourselves here, the velocity of A in the x direction initially, well, that's just indeed the velocity of A period initially, which was our 40 meters per second. And the velocity of A in the y direction initially was just 0. And the velocity of B in the x direction initially was equal to the velocity of B in the y direction initially, which is also 0. These x and y components of the final velocities we can turn into just the final velocities times some sine and cosine terms in the usual manner. So we could say that the velocity of A x in the x direction final would just be velocity of A final times the cosine of 30 degrees, because the x component is going to be the adjacent side, and the velocity of A in the y component would just be velocity of A final times, in this case, the sine of 30 degrees. And similarly, the velocity of B in the x direction, that's going to be the velocity of B final times, well, in the x direction, that's going to be cosine of 45 degrees. And the velocity of B in the y direction is going to be minus VBF times the sine of 45 degrees, minus because the y component of B is downward while the x component of B was forward, and the x component of A was forward and the y component of A was forward. But this one here is a negative sign because of, let's see if I can adjust the glare there. There we go, that's better. There we go, much better. And so now we can take our x and y momentum equations and write them down in terms of just the total velocity. So again, our x momentum equation, let's go ahead and write it down here, give ourselves a little bit of room. x momentum, that's going to be, oh, one other thing that we haven't taken into account here is that mass A and mass B are the same, so let's just call them mass. So we've got mass times velocity A initial equals mass times velocity A final cosine of 30 degrees plus mass times the velocity of B final cosine of 45 degrees. And the mass terms cancel, and we can go ahead and replace the initial velocity with 40 meters per second, and the cosine of 30 is 0.866, so 0.866 times VA final plus the cosine of 45 degrees, 0.707 times the velocity of B final. So that is one of our momentum conservation equations. And we can write down the other momentum conservation equation for y here. What we had left up here was just 0 on the left is equal to just mass times, that's going to be VA final sine of 30, and then minus mass times VB final sine of 45. And again, the minus sign here is because the y component of B final is negative, like we had over there. And we can move the B term over here. So sine of 45 is also 0.707 mass of VB final is going to be the sine of 30 degrees is a half, 0.5 times velocity A final. And we can just solve this for the velocity of B times the mass. And the mass terms cancel. And we can just solve this for the final velocity of B in terms of the final velocity of A. Divide a half by 0.707, and you get 0.707. That 707, of course, being root 2 over 2 is velocity A final. And if we go back to this equation and bring it over with the replacement of this, so again we go 40 meters per second is equal to our 0.866 final velocity of A plus 0.707 times 0.707 velocity A final, where we took this and plugged it in for velocity B final. So that's 0.866 VA final plus 0.707 times 0.707 is again a half VA final, which is 1.366 VA final. and that's equal to 40 meters per second. So if we take the 40 meters per second and divide by 1.366, we get 29.3 meters per second, and that's the final velocity of asteroid A. And then once we have that, we can plug that in up here and see that the final velocity of asteroid B is 0.707 times our 29.3 meters per second. So our velocity B is 29.3 times 0.707, 20.7 meters per second. So our two velocities here, as I predicted earlier, A has to be moving a little bit faster than B was because B had the steeper angle. So the next question, the next thing that the question asks is what fraction of the original energy of asteroid A dissipated during that collision? Well, so what we're asking here is before the energy, or the initial energy, is just 1/2 times our mass times the initial velocity A squared. And our final, or energy afterwards, is the kinetic energy of both of those. So 1/2 m VA final squared plus 1/2 m VB final squared. And we could calculate basically the ratio of the energy afterwards to the energy beforehand. So energy after over energy before, well, that's going to be our two kinetic energy terms, 1/2 m VA final squared plus 1/2 m VB final squared, all of that over our initial 1/2 m VA initial squared. And the 1/2 m terms all cancel. So this is just VA final squared plus VB final squared over VA initial squared. So that's going to be our energy after over energy before is 29.3 meters per second squared plus 20.7 meters per second squared over 40 meters per second squared, and 29.3 squared plus 20.7 squared, that's 1287 or so meters squared per second squared on the top, and 40 squared on the bottom is 1600 meters squared per second squared. So that ratio is 1287 0.80. So in other words, energy after is 80% of the energy before, or we lost 20% of the energy. Okay. All right, so other than we have to keep track of twice as much stuff, and we get a system of two equations to deal with, typically out of these things. The same sort of logic that we were using in one-dimensional collisions still applies. We just have to do it in 2 dimensions at the same time. All right, so let's try another example here. This time not just an inelastic collision, but a completely inelastic collision. So our problem says 2 automobiles of equal mass collide at a right angle in an intersection. After the collision, they remain joined together and skid with locked wheels before coming to a rest. The length of the skid marks is 18 meters, and the coefficient of friction between the locked wheels and the pavement is 0.8. What was the speed of the conjoined cars immediately after the collision? And if the conjoined cars move in a direction 30 degrees from the original direction of one of the cars, what were their original speeds? All right, so let's draw ourselves a picture here. We have a car of mass m moving at a speed va, or a velocity va in that direction, and a car also of mass m moving at a velocity vb in that direction. And there's a collision, so this is before, and afterwards we have moving at some velocity v final at an angle here, theta of 30 degrees. Let's bring the brightness down just slightly. From the original direction of motion. All right. We've been told that there's a coefficient of friction here of 0.8. The distance traveled is 18 meters. And that's pretty much all we've been told. All right. Well, this business over here of the distance being traveled and a coefficient of friction, that's a work energy problem, right? So this is a fairly standard thing. We've seen this a number of times now. The mass, or the size of the friction force here, the magnitude of the friction force is going to be mu k times the magnitude of the normal force, which in this case with a horizontal road is just going to be the weight of the combined 2 cars. So twice the mass times g, that's the magnitude of the frictional force. And the frictional force is going to be in the opposite of the direction of motion, as is typical for friction. So we can say that the work done is going to be minus the friction force, mu k, times 2mg, times the distance, d. And we're going to start that motion with a certain amount of kinetic energy, and we're going to end it with 0 energy. And so the change in energy is going to be minus 1/2 times, again, 2m times v final squared, the kinetic energy just after the collision. So the minus signs cancel, the 2m's cancel, and we're going to look here for v final squared, and so 2 mu k times g times d is v final squared, and so the square root of that, square root of 2 mu k gd, is our final velocity just after the collision. And we can plug in some numbers here. That's going to be 2 times our mu k is 0.8 times 9.8 meters per second squared times 18 meters, and that turns out to be 2 times 0.8 times 9.8 times 18. Take the square root of that. Oops. 2 times 0.8 times 9.8 times 18. There we go. Take the square root of that. And that gives us 16.8 meters per second is the velocity of our conjoined cars right after the collision. If this angle here is 30 degrees, then we can use momentum conservation here, and the horizontal component, or x momentum conservation, is going to look like, well, m times VA is equal to twice m, because we have an object here of 2m moving at velocity v final, but it's only the cosine theta, so the x component of that. And similarly, the y momentum looks like m times vb, and 2m vf sine theta, so the vertical component of that. And we can go ahead and plug in numbers then. So the masses cancel on both sides, and VA then is 2 times VF, which was 16.8 meters per second, times the cosine of 30 degrees. So 2 times 16.8 times the cosine of 30 degrees gives us 29.1 meters per second for A. And velocity B is 2 times VF sine theta. So that's 2 times 16.8 meters per second times the sine of 30 degrees. So 2 times 16.8 times sine of 30 is 16.8. All right, so again, in this case, the information gave us enough to sort of work the back end first, and we calculated sort of from a work energy problem what the initial or the final velocity after the collision must have been, and then we used the geometrical information to write down x and y versions of momentum conservation, conserve the x momentum, conserve the y momentum, and then plugged in the numbers to get our initial velocities. All right, let's do another one of these. And adjust the brightness here. See if we can make that a little bit more visible. Well, I don't know, that helped. Yeah, we'll go with it. All right. It says, a watermelon is blown into 3 pieces by a large firecracker. 2 pieces of equal mass fly away perpendicular to one another, one in the x direction and another in the y direction. Both of these pieces fly away with a speed of 39 meters per second. The third piece has 3 times the mass of the other 2 pieces. What is the speed of the larger piece in meters per second? And what angle does the larger piece travel with respect to the minus y-axis in degrees? All right, so the first thing to note is that this is not a collision per se, it's an explosion. But if you think about it, it's kind of like a perfect inelastic collision in reverse. So remember, the perfect inelastic collision, that was the one where you had two objects smash together and stick and form a combined object. What we have here is a combined object which explodes into different pieces which fly apart. Again, momentum conservation is going to hold here. There's no external forces at all acting on this system. And so the momentum beforehand, which in this case is 0, must be the total system momentum afterwards. And again, in general, explosions are basically perfect inelastic collisions in reverse. And they work exactly that way when you work the problem. So in this case, we have an object afterwards of mass m moving in that direction, another object of mass m moving in this direction, both at speed v, which is 39 meters per second. And then we have an object here of mass 3m moving at some speed v3 and at some angle here, theta, relative to the vertical axis. All right, so the x component of momentum, let's look at the x momentum conservation. The initial momentum in the x direction was 0 times the total mass, 0 velocity times mass plus 3 times mass. Excuse me, still just 0 on the left. And that's got to equal the horizontal component of, well, this is mv, that's some horizontal momentum, there's none of that, and then minus 3mv3, and it's the opposite, so sine of our angle theta. And so we can equate these two, so the mv must be 3mv3 sine of theta, and the masses cancel, and that v must be equal to 3v3 sine theta. All right, so that's the horizontal momentum conservation has led us there. Vertical or y component of momentum conservation is going to give us, again, 0 on the left is equal to, well, m moving at v upward minus 3m v3 cosine theta, because that's the adjacent side. Negative because it's pointing downward. Again, we can set those things equal since this difference is equal to 0. So mv is equal to 3m v3 cosine theta. The masses again cancel, and we're left with v equals 3v3 cosine theta. But it was also equal to 3v3 sine theta, which means that cosine theta must equal sine theta, and that one should be familiar to any student of trigonometry. Theta must be 45 degrees then. So once we know that, we can plug it back into our speed v equals 3v3, say sine theta, solve this for V3. So that V3 is going to be V divided by 3 times the sine, in this case, of 45 degrees. So that's 39 meters per second over 3 times the sine of 45 degrees. So 39 divided by 3 divided by the sine of 45 is 18.4 meters per second is the speed of our larger chunk of watermelon, and it's moving off at a 45-degree angle from the other two. So again, explosions are just collisions in reverse and need perfect inelastic collisions in reverse. You still conserve momentum, and if you have multiple dimensions, you conserve momentum in multiple directions at once. All right, so we've looked at perfect inelastic collisions. We've looked at non-perfect inelastic collisions in multiple dimensions. What does an elastic collision look like in multiple dimensions? And the answer is, well, it can be a bit ugly. An elastic two-particle, two-dimensional collision. This is basically one step up in elastic collisions from the one-dimensional collision. And we already saw that the one-dimensional elastic collision was kind of an algebraic mess. And this is not going to be any different. We have to conserve momentum, and we have to do it in each dimension separately. So if we have a 2D collision in x and y, we have to conserve the horizontal momentum of our two-particle system and the vertical momentum of our two-particle system. So we have momentum of particle 1 before plus momentum of particle 2 before in both the x and y components. We have the momentum of particle 1 and the momentum of particle 2 after in both the x and y components. So we've got two equations, each of which has 4 terms. Just to do the momentum conservation, and to add on to that, we then also have to conserve energy, which means we have 4 kinetic energy terms. And so we've got 2 masses, 4 velocities, so that's 6 parameters, and we've got 3 equations. Now there's only one energy conservation equation because, again, energy doesn't have any direction information. It's a scalar quantity. So there's no directional information. Unfortunately, also, kinetic energy goes as the square of velocity, which means that we are inevitably going to be left with a quadratic equation mess of some sort, combining these 3 sets of equations to then solve for things. So, like we saw with one dimension, we have to be very careful about making sure that we get the signs of each of these velocities correct relative to their direction. So if it's going up, it's going to be a positive velocity. If it's going down, it's a negative velocity. If it's going to the plus x direction, it's positive. If it's going to the minus x direction, it's negative. So we've got to worry about all those plus and minus signs in the x and y momentum conservation equations. Plus, we've got squares of all those velocities showing up in the energy conservation equations. So this is going to explode algebraically. There's no way that that cannot be true. This is always going to be an unfortunate algebraic mess. Let me suggest that one thing that you can do is anything that you can turn into a number, do it early typically in these things. Break things up into their numbers as soon as possible. Turn sines and cosines into numbers If you know any of these velocities, turn them into numbers. If any of those velocities are zero, hallelujah, because that'll blow holes in some of these terms. But in general, solving multidimensional elastic collision problems is always an algebraic nightmare. So go slow, be prepared to blow lots of paper. Generally, you're probably not going to run into a two-particle 2D collision that's elastic in the context of uh, something like an exam for a course like this, because usually the algebra just gets too ugly and too hairy. And again, we're not testing physics at that point, we're testing algebra manipulation. Sometimes for certain situations, like for instance, if all the masses are the same, that can simplify things. If there's some nice symmetry, or if one of the particles wasn't moving to begin with, then it can simplify enough that it doesn't get too hairy and it doesn't get too much worse than, for instance, the 1D elastic collision problems. But in general, it's just like elastic collision in 1D, except with even more algebra. We're not going to go ahead and we're not going to do an example of this here today, but should you run into one of these in the wild, this is sort of my rule of thumb. You conserve momentum, you conserve energy. You could, in principle, write down the generic solution for a two-particle 2D collision, but it's super, super ugly. I don't really think it behooves us to go through that too much. So there you go, two-dimensional collisions in their inelastic and elastic forms. All right,